Hello, welcome. We are going to try to apply the conservation of energy to analyze and explain energy transformations today. So recall, for any object that's moving, we say that it has kinetic energy. And the formula for kinetic energy is equal to 1/2 times the object's mass times its speed squared. So energy is measured in joules. Mass, our standard units are kilograms, and speed meters per second. If an object has any height above a particular surface, we say it has gravitational potential energy. Gravitational potential energy is equal to the object's mass times this gravitational constant we'll talk about in just a moment, times the object's height. Again, gravitational potential energy, it's an energy, it's measured in joules. Mass is kilograms, height is meters. Now this gravitational constant, the units are meters per second squared. And I'll talk a little bit more briefly about this value. At sea level, this value, Earth's gravitational constant, is approximately 9.8 meters per second squared. So that's the value that we'll be using for our calculations in this course. It's really interesting to note that this value actually changes depending on where you are in the world. So here is Earth's gravity measured by NASA, and it just shows deviations in Earth's gravitational field. This table just alludes to it a little bit more. Notice, depending on where you are in this world, our gravitational field strength is going to vary slightly. And this is information that if you go on and study Physics 11, AP Physics, Physics 12, these values, you'll be able to actually calculate them yourself, depending on the radius from the center of the Earth and the mass of the Earth. Note that also on Earth, right, we might have a 9.8 meter per second squared acceleration or gravitational field strength. But on different planets, we're going to have vastly different numbers. So Jupiter, we have 2.5 times that value. And again, this just depends on Jupiter's radius and its mass as well. For our cases, 9.8 is a pretty good approximation. So let's just stop this skater for a second, and let's look at this, or try to think about these two questions. How do these energies change in the following simulation, and how can we represent this as a mathematical expression? So I'll pause this. Notice as the skater gets lifted higher, the potential energy increases. And this potential that it's referring to, that blue bar, that's referring to gravitational potential. Potential just means stored energy. It can be stored in a variety of matters. You can have electrical potential energy. In this case, it's gravitational potential energy. And as this skater gets increased, their gravitational potential energy also increases. Notice right now, all of their energy is just stored as gravitational potential energy, or at least that's what this simulation is showing. So as we play this simulation, you'll notice the potential energy is changing, kinetic is changing, but the total energy doesn't change, right? That is the law of conservation of energy. Energy isn't created or destroyed, it's just transferred from one form to the other form. That's going to be the key for our calculations. So, one other thing to note before we move on is that in this situation, we're not including friction, right? If we were to include friction, we would notice that some of the energy would be converted to thermal energy. So for the purposes of this video, we're going to look at a simplified model, and that simplified model is no energy is converted to thermal energy whatsoever. Okay, so this is the question we're going to explore right now, and that is, what is the speed of the skater when they're 2 meters above the ground in this situation that we have here? So here we have a skater. They're starting at 6 meters above the ground. At a different point in time, they're 2 meters above the ground. They've got some kinetic energy. They're moving. They still have potential energy. They're at some height above the ground. So what's key to note is that these yellow bars, the total energy, hasn't changed, right? The total energy in both of these is exactly the same. So we can write that out as a mathematical expression saying the total energy at this location is equal to the total energy at this location. So we call that just initial and final total energy. Now, what are the various types of energies that we can have? Well, we can have kinetic energy. We can have gravitational potential energy. In this case, we're ignoring thermal energy, but that's a possibility too. So we could have kinetic energy. Now, you might be looking at this right off the beginning and go, well, that value is just 0, right? This skater is just at rest at the highest point. There's no kinetic energy. And that's true, but I'm just going to show you through the calculations why that value is 0. They do have gravitational potential energy at the beginning, right? That's this blue bar. And the final, at this location, they have kinetic energy. They have gravitational potential energy. And again, we're going to ignore thermal. We're going to say thermal does not exist for this simulation. So our formulas, we have formulas for these various quantities. Kinetic energy, we talked about, was 1/2 times the object's mass times its speed squared. That I right here just refers to initial. Rather than writing out the word initial every time, we're just going to use the letter I. So we have our formula for initial kinetic energy. We have our formula for initial gravitational potential energy. We have a formula for final kinetic energy, where F refers to the final. And we have a formula for final gravitational potential energy. Now, this value for the kinetic energy was 0 because its initial speed at the highest point of this ramp is 0 itself. So 0 times any number is just 0. This term we can completely ignore. It does have gravitational potential energy, where 6 is the initial height, 6 meters above the ground. So I'm omitting all of the units for this case just to simplify it. But if you'd like, you can include units in the 6 meters, and then here we have 9.8 meters per second squared. If we want to figure out what the speed of the skater is when they're 2 meters above the ground, really that's what we're trying to find, is this final velocity. What is that final velocity? What is the velocity at this location? And we have a height of 2 meters above the ground at this location. So it has gravitational potential energy in its final location. From here, let's just clean this up a little bit. And what I would do next is, I notice that there's a mass and m in every term. So we can divide both sides by, mass. Mass, m divided by m, is just 1. So 1 times any number is just that number itself. Similarly, we can have this mass divided by that mass, this mass divided by this mass, and we get the following equation. From here, I mean, really, this was the physics, right? The rest is an algebra problem. So now we're just trying to find what is this final velocity. So the next thing I would do is subtract that from both terms, or both sides of the equation, I should say. And then from here, you can either multiply both sides by 2 or divide both sides by 1/2. Both work. The last thing we need to do is take care of this square, which would be taking the square root of both sides of the equation. And we find our final answer, 8.9 meters per second. So this is super powerful because we started with the object at 6 meters above the ground. So if you know the initial height of an object, you can make a prediction about what that object's speed will be at a different height. So this provides you with the tool to solve problems. So our learning objective was, I can apply the conservation of energy to analyze and explain energy transformations. Hopefully you can do that a little bit better now, and thanks for watching.